So today we're going to be talking about continuously compounded interest. So we talked about compounding. So what if you broke it up to say, yeah, it's 4%, but we'll do 1% every 3 months. So it's still 4% at the end of the year. If we break it up and said, I'm going to take that 4% and break it up infinitely, but give it to you infinitely. Break it up down to every second, but I'll give it to you every second. And so to do this, we're going to get into some crazy stuff, an irrational number, just like pi. So I ask, what is I? I we use to represent the square root of -1. Pi is a representative of 3.14159, etc. So there's a difference between these two. This is imaginary. This is something mathematicians came up with to represent something that's essentially impossible. This is something that mathematicians came up with to represent an irrational number. That's when you have an integer divided by an integer that produces this like impossibly long, never ending, never repeating value. So you learned about pi, probably before geometry last year, but you certainly saw it a lot in geometry last year. Well, now you're going to see more of it. Right? So here we have irrational numbers. Right? We have whole numbers, we have integers, and we've got irrational numbers. And outside of that plane of thought is irrational. That's what E is. So the natural base is what it's called. It's also called Euler's number. That's where we get E, Euler's number. That's the guy who was smart enough to figure it out. And it comes from saying, as you do this, 1 plus 1 over some number to the power of that number, you keep getting closer to this. And I would encourage you to try this on your own. Try 5, try 10, try 100. Watch what happens when you start doing, okay, 1 plus 1 over 100 to the 100th. When you start doing 1.01 to the 100th, and you can imagine it's only going to get, this is only going to get smaller and smaller as we get more towards if it's 1 over 1,000, 1.001 to the 1,000th. So this number is going to get bigger, this number is going to get smaller. What's going to happen is you're going to keep getting closer and closer to 2.718281828. So, what is the point of this? How do we use it? Because it's representative of this, this is what we talked about, right? What if I told you that you're going to take the growth rate and divide it by an infinitely large number, but then have it occur an infinitely large amount of times? So it allows us. So, and here you can see, right? This is the idea I was going for, right? Like as you turn this into bigger and bigger numbers, you'll get closer and closer to actually being E, right? We're going to use it in its own equation for continuous compounded growth. So we're going to have an equation that's almost separate from our compounding equation. I just want to talk real quick. E, it's called the natural base. You'll see, when we get talking about logarithms, it'll make a lot of sense, but that it works like any other number, right? E squared times e to the 5th, you go, oh, that's e to the 7th. So this is just a page on reminding you, don't freak out when you see e. It's just a placeholder for any other number, just no different than 2 squared times 2 to the 5th is 2 to the 7th. This is, just a placeholder for 2.718 and all that good stuff, all right? So let's push into actually dealing with continuously compounded interest, right? It's going to look like this. The answer, or the amount, is going to be the principal, right? We're used to having P be principal, times e to the power of rate times time, times p to the power of rate times time. So it's essentially saying your principal amount, say it's $100, times e, which is 2.8. I mean, really, it's even better to think about it as times 1 plus 1 over n to the power of n, and we know power to a power that's multiplying times the rate times time. And this is what's happening if you're dealing with continuous compounding over the course of years and years, right? And that this is essentially represented by E, because it's essentially 2.782, all that good stuff. So compare this to 6% of fixed interest. You get 6% annually. Well, what if you compounded it continuously? Right? What if you used E to the power of 0.06 times a year versus if you just did 4,000 times 1.06 for a year? Gonna wind up with slightly more money. And again, we've talked about this before. Sometimes it'll seem so minuscule. Like, look at this. If it's just $1,000, the difference between annual compounding, right, and monthly, you go, oh, I made an extra $3 monthly. And if it was continuous, I made what, an extra 29 cents, Mr. Card? Who cares? Well, you care if instead of 1,000, that's a million. If instead of a million, that's, oh, I don't know, a billion, right? Bezos bucks, right? Stuff he doesn't even care about losing. But what's that 0.29 turn into? Suddenly that's more representative of like millions of dollars, hundreds of thousands of dollars. More money than the average American makes in a year. So why is E so important? Obviously the continuous compounded interest, but we're going to talk about it being the natural base of a logarithm, which we're going to introduce next week. For now, I just want you to be able to set up problems like this yourself and solve them. To be able to say, okay, 5,000, 5%, continuous, 5 years. That's because I see the word continuous, I got to think I need that E value. So it's 5,000 times E to the power of 0.05 times 5. So if you're curious how you can actually get E on your calculator, it actually should have its own button just like pi. I'm curious, I'm looking at my phone calculator right now. Yep, there's an E button, right? So you have the ability to do E to the power of 0.25 on your calculator. E is the power of 0.25. And then multiply that by 5,000. Look at that. $6,420.13. Right. So this is very doable. And I hope you feel, after watching this video, you have an idea what E is, where it comes from, which is just the idea of what if you were constantly taking the rate and making it smaller, but what if you were also constantly getting that rate, like literally at all times? So it's about this number going towards infinitely large numbers. But I'll stop the video there for now. Next week, we get into logarithms.